the current on a transmission line. A transmission line can be described by these two equations. There is a magnitude of positive voltage multiplied some phasor form, which is a function of propagation constant and the position. So this is the form of your voltage at different position. What is the voltage at a different position? Okay, but in the real world it's not. You think it's moving, right? Because you haven't multiplied exponential j omega t yet. So the voltage on your transmission line is changing depend on position and the time. Different position, different location, and according to different time, it's moving. Okay, this is the voltage and also the current on the transmission line. Okay, this is the first thing we learn from this week in this class. The voltage and the current the magnitude of positive voltage over the magnitude of positive current. We define this ratio as the characteristic impedance. If we say 50 ohm means your magnitude of this positive wave over magnitude of the positive current, voltage of current, the ratio between these two, it is 15 ohm. It will equals to the magnitude of negative voltage over the magnitude of a negative current and multiply. You take a minus sign. Okay? And also, your Z0, as we derived so far, it is equal to this equation, this function. The square root of this, they are the lumped average value of the transmission line. This one can describe what is Z0. Okay? This is what we learned so far. And also, here, when we write down the voltage and the current function, you have the phasor form, the gamma. The gamma term, you can describe your gamma term using the lumped values as well. Okay, you can use R, L, G, C to obtain your gamma and Z0. Okay, you can obtain your from both of them. Right now, let's try to check the lossless transmission line. Okay, extra point. What is the gamma of for lossless transmission line? What is gamma and then what is Z0? Can anyone help me? Can you answer two? It's not very difficult. So gamma is
约一下。
Yeah, make it more beautiful. Also then, you can do that.
你先约分上面的。你刚好先约分，下面就可以带入了，比较好算。
Just give him more time. It's very a lot of pressure when you come here, right? You can do that maybe later, but you want extra time maybe. Let's do the, okay. So how about the first one? Can you simplify the first one? So equals to, can you take a square root of -1 to j? You do that? And there is omega squared, right? Can you take omega squared outside? And then the -1 take a square root is equal to j, right? And okay, can you write down that equal to j beta? This one equals to j beta, right? For a lossless case, j beta. Okay, so beta equals to okay, very good. Okay, correct, right? Yeah, extra time. Very good. Okay. Yeah. If I tell you the average inductance and the average capacitance of a transmission line, you will know the propagation constant and the characteristic impedance of the transmission line. Okay? This is how we use it. For the lossless case, it's easy to understand, right? It's very simple. So, okay, moreover, now we know the ratio of this one to this one, right? So actually, we can use this notation Z0 instead of I0 plus and I0 minus, right? You guys understand? Because Z0 equals to this one, and then Z0 equals to this one, right? So we don't need to use I0 plus and I0 minus. We don't use it. We can use this relationship. We can transfer my current to some parameter of voltage divided by my characteristic impedance and take care of this sign, okay?
Minus.
Yeah, this is the minus sign. Minus, because that is the ratio of the I0 minus, there is a minus sign. Okay? So this is our new voltage and the new current when we know the characteristic impedance. Can I get you more? Okay.
after we know the new voltage and the current, this is a relation. This is what we learned so far, okay? Gamma equals to alpha plus j, beta equals to this, z0 equals to this, and beta, this is what we learned before, right? And this is Vp, what we learned before. And I already asked you the questions. You already give me an answer. What is the lossless line? In your textbook, they give you what is L and the C and the R and the G for coaxial cable. For coaxial cable, your L has a function of the radius of the inner conductor and the outer conductor. Okay? And then there is a mu. This mu is relevant to the material between these two conductors. For the C, 2 pi epsilon. This is epsilon r. Okay? I think it's epsilon r, or maybe epsilon. It's the epsilon. Over natural log B over A. Okay, you can see the material inside relevant to epsilon prime, and also the radius, outside radius and the inside radius. If that is a lossless coaxial cable, the question I will ask you maybe just lossless. You use the LC here to derive everything. What will I tell you? I only tell you I give you this. I tell you I have a coaxial cable and I have a geometry of the inner radius and the outer radius. Okay? I tell you the material, the white part. What is the material? Okay? Tell me voltage and the current. And that's it. Tell me all the voltage and the current on this transmission line. Can you do that? Okay, tell me if you can do that in the final exam, okay? Everything is connected, right? You can solve everything. And maybe I can also ask you what is, I will ask you what is the phase difference if my physical length is something. If I give you this kind of transmission line. I give you the material, I give you the geometry. You need to give me others. Okay? Okay? Give me voltage, current, anything else. Or maybe I give you voltage, I ask you about the current. I should give you the magnitude, right? I give you a voltage, the function of voltage. Tell me what is the current of this transmission line. Because you know LC, you know propagation constant, you know characteristic impedance, you should know everything else I want. Imagine what will happen in your final exam, what kind of question I will ask you. Okay? Okay? You need practice? You will have, I think in your textbook they have example about what I'm talking about. They have example about the cohesion. I will not ask you these two wire line and parallel paths. Maybe you won't use it. But for coaxial, it is important. There are some company in Thailand, they manufacture a lot of connectors. They use these equations a lot. If you know this one, you know how to design a connector, and maybe you can have your own company. Okay. Yeah, a lot of companies they make the connectors. It is coaxial connector, right? Coaxial connector. Those are the key equations. They will use like a 50 ohm, maybe use 100 ohm. Remember, they use these equations.
75.
Okay, 75. Yes, 75 ohm. They use the same equation. You want to design the geometry. You need these equations. Okay, let's stop here and then we discuss about when to discuss, or maybe you can directly come to my office to discuss about to see your midterm, okay? Because we have a little time, I don't have enough time to finish the second part. We need a long time I don't want to cut in the half. It's just time wasting. I need to finish together. So, and I think you guys need to rest, to digest. And you can come to my office now, and if you want to see your midterm, okay? Okay, so that's it for today's class. Any question about this one? It's a long derivation, right? It's long derivation, but maybe first time, but it's very useful. It's very useful.